projects I've done that are calculator related with the 6502 processor. I was here 2 years ago and gave a presentation about this and talked about some of my old projects, and this will be about the projects I've done in the past 2 years since then. So today I want to tell you about the 6502 processor. I'm sure a lot of you guys already know about this. You've probably used it or even own those machines if you're into retro computers. I'll tell you about my 2 old projects I already presented on just briefly because the new projects are built on that, so it's good to understand that to understand these. And then the 3 new things that I've done since then. So just briefly about the 6502. It was really important in computing history. It helped launch the computer revolution, used in the first 2 Apple computers, the first Atari video game system, Nintendo Space Shuttle. It was used in the Commodore 64 in the 80s and a bunch of home computers. In the 90s, it was used in toys like Tamagotchis and Furbies. And it's still in use today. It gets used in stuff like hard drive controllers, radios. I'm told every pacemaker sold in America has a 6502 in it. They sell hundreds of millions of them per year, so they're easy to get and relatively easy to use. So if we look at the specs of the processor, if you're curious about building a calculator with it, you can see that it's really old. It uses old NMOS transistors, which are very power hungry, not very efficient. It requires 5 volts to run. Newer processors will run at 3 volts or even 2 volts or less. It has a huge current consumption. If you think about a coin cell like you have in a DM42, you can draw about 10 milliamps at 3 volts. So you'd need like 15 coin cells just to run the processor. And that doesn't include the RAM and the ROM. And the speed is only 1 to 2 megahertz, so not very fast. So when I gave my presentation 2 years ago, somebody came up to me and said, "Why are you using such an old, terrible processor to build your calculator with?" And so what I should have told him that 2 years ago was, when I say 6502, what I really mean is the new 6502. That uses more modern CMOS transistors, so it'll work down to 1.8 volts, which is really convenient if running on a battery. It takes 100 times less current, so you could definitely run it on a coin cell. And it's much faster. It'll go up to 14 megahertz. So it's not like hundreds of megahertz like a Prime, but it's a decent amount of horsepower. If you compare it, for example, to a Z80, which is what TI puts in their TI-83 that they're still selling, that runs at 6 megahertz, but because the clocking is different, it's equivalent to about a 1.5 or 2 megahertz 6502. So if you built a processor with this, it'd be 8 or 9 times more powerful than a TI-83, which is not bad. So the first old project I already presented on that I want to tell you about is my simulator. I built a processor simulator that works in your browser. This is a screenshot of a version of BASIC I ported to work in that. So if you go to my website, you can get a BASIC prompt. You don't have to download anything. It's really neat when you want to develop software because I built a lot of things in there, like you can see the registers, you can see the memory, you can step cycle by cycle and see what the processor's doing. Here's another thing that I already showed. It's a Mandelbrot program someone had made in BASIC, and I got it to run and added color, just for example, to show what my simulator can do. And one new thing that I've done since the last time I was here is I ported a version of Forth that will run in that. So you can get a Forth prompt if you go there. It runs in your browser.
Isn't there
Yes.
the particular register architecture and instruction set of the 6502 has things that support stacks, which are very important in Forth. And at one time when I used to be active in the Forth interest group, the 6502, that was the ultimate thing to have.
Right. So
Except of course for the memory limitation.
Right. So I think the Fig Forth was the really popular one back then for the 6502.
Yeah.
Yeah. Okay, so that's the first old project, and then the other old project I wanted to show is an optimizer I made that will take your assembly program for the processor and it will make changes to make it run faster. And so if we look for a second at the registers that 6502 has, the A register is the main register that does all the interesting stuff like adding, subtracting, shifting, ANDing, and ORing. And then the X and Y registers are just helpers. They can't do any of that stuff. They can only increment and decrement, and then they can address into memory. So if you look at the way that a lot of programs work, like in assembly and C, usually when a function starts, it'll adjust the stack pointer down to make some room. Then it will store the local variables temporarily on the stack. So to be able to do this, you need a processor that can address the memory relative to the stack pointer. So you could say, if I want variable 2, you tell the processor, give me the byte of memory that is 2 bytes beyond the stack pointer. Unfortunately, 6502 doesn't have that addressing mode. You can't address memory relative to the stack pointer. So in order to have this mechanism, what a lot of people do is they dedicate their X register to be a data stack. And that works pretty well, but it has some disadvantages. So you lose your X register, and that means you have to write all your programs with A and Y, which is not a deal breaker. You can still do anything you need to do, but it's less flexible, it's a bigger code, and it's slower when you don't have the X register since you've lost it as a data stack pointer. Also, when you address things relative to the X register, it adds an extra cycle. And the 6502 is relatively cycle efficient. It can load a byte from memory in 3 cycles. So if you add a 4th cycle, percentage-wise, that's kind of a big slowdown. And then the last thing is that anytime you enter and leave a function, like I showed on the last slide, you have to adjust the stack pointer, which is not a big deal, but it adds a little bit of overhead. So the optimizer I made solves these 3 problems and gives you back your X register. And the way that it does that is it goes through the program and it builds a call graph to see what functions call which, and then it looks at how much memory each function uses. And then using that information, it can determine a fixed location in memory to store the local variables. So you see here this second byte, there are 6 different colored blocks. That's because 6 of the functions on the last slide all share this byte of memory. That's because if you look at the call graph, they never call each other, so they never step on each other's memory. So another word for this is a pre-computed stack. And so that's the second old project I wanted to show, and the first new project I want to show is trying to figure out, well, so what? So I saved a few cycles, but did this really do anything? Am I just making my calculator programs like 1% faster? Because if that's the case, then there's probably no reason to go through all this hassle to generate the call graph and all this stuff. So I thought, how can I compare this old style of assembly and the new style the new optimized that I created? And I was also curious what the performance is like between these compared to C and Forth, which are 2 other languages you can use to write code for this processor. And so I thought, if I want to figure out the difference in speed, I could do some type of benchmark. So you could do Cordic, like you use to figure out sine and cosine, or a solver like Newton-Raphson. I thought about maybe the Inqueen benchmark or something like more traditional, like the C benchmark. But honestly, that sounded a little bit boring. So instead, what I did was I made this video game. I made this in Python on my computer, and then I ported it to each of those 4 languages, assembly, C, and Forth. I remade it 4 times for the 6502, so that would give me something to benchmark. So in the game, you explore this little map on the right. You have health, battery power, and you gain experience for doing things that lets you improve your character. You can walk around. There are evil robots, there are minerals that you can harvest, and then there's lava that will kill you if you step on it. There is a character screen where you can get new items, and when you equip them, they'll change the look of your character and also change the stats. There is a skills page where when your robot gets upgraded, you can choose ways to make it better, and then a resources page. So as you collect crystals, you can buy new things that improve your robot. So if you're not really into video games, that's fine. You don't have to understand how the video games work. It was just a chance to write a useful program that I could use to benchmark and see the cycle differences. So, like I said, I did this once for each version. So this is the traditional assembly, optimized assembly, C, and Forth. And if I did it correctly, they should be pixel for pixel identical to each other. So after I finished that, I looked at the different tasks that the game accomplishes internally. So for example, all of the graphics are stored with run length encoding. They're compressed. And so I timed how many cycles it takes to decompress an image into RAM. I also looked at how long it takes to add color to the images, since the rock, the lava, and the dirt are all the same. They're just colored slightly differently. I also timed how long it takes to rotate images in memory. There are 4 different dirt tiles, and the flecks are colored differently, but it's the same graphic. It's just rotated at different degrees to give the game some variety. So I did all that. All in all, I looked at 27 different things that the game does. And this is the graph I came up with. So the traditional assembly I showed before is normalized at 100%. So anything above 100% is faster than the old assembly, and anything below that is slower. So the optimized assembly is in blue, and as you can see in like maybe a quarter of the cases, there's not much of a speed upgrade, but a lot of cases you get like a 10 to 12% upgrade with optimization. So I think that's enough of a speed boost that I'll keep doing it. I'll keep using that. The red lines are the C compiler. As you can see, it's maybe 2 or 3 times slower than assembly, which is kind of an anomaly. Usually C compilers produce really good assembly, but for the 6502, that's tough. And so, unlike most processors, it's slower. And then the Forth is in the orange, which is down at the bottom. fourth has a lot of advantages. The code tends to be a lot smaller, but unfortunately there's a huge speed penalty that you pay. So that's the first new thing I did. I got some useful information about other stuff I want to do going forward. So the next thing I want to show you that's new is a new calculator I started building. So I've got as far as the RAM, the ROM, the processor. I can boot. I need to add a keypad and a battery, but I have a screen going. It's 128 by 64 LCD. It's a graphic LCD, so I'll be able to draw graphs with it. And so the processor in this is not the old crappy 6502 that you should not use. And it's also not the new one that is relatively fast. It's something that's even worse than both of those, which is a 6507. It's the same old, very power-hungry 6502 from the 70s, but it has some of its pins removed to reduce functionality, and they did this to save money. So as a result, you can only address 8K of memory instead of 64, and you don't have any interrupts. And so why would you use such a terrible, horrible processor? And the reason I agreed to do this is because on the 6502 forum, there was a guy who had a bunch of these from the 70s, and he agreed to send them out for free as a friendly competition, so that to see what people could build out of it, just out of curiosity. And because I like calculators, I agreed to build a calculator. And so what he sent us was the processor, the 6532 Riot chip, which has 128 bytes of RAM, which even for a little calculator is not enough, so I added another 2K of RAM. It has 16 bits of I/O, which is really important since the processor doesn't have its own I/O. I use this to drive the LCD and to read the keypad. And then it has a timer, which is important. When you don't have interrupts, you need some kind of way to time things. And then he also sent us this old 2716 EEPROM, which some of you may be familiar with. You can program it. It takes a really weird voltage, I think 18 volts or something.
25.
25? Okay, 25 volts. You can write to it once, and then you have to shine UV light down into the window to erase it.
Yeah, and
Yeah.
keep it covered if it's in
Right.
requirement.
Right. So I was happy to use this old processor, but that was kind of like farther than I really wanted to go, to be honest. So we talked to the organizer, and he said it would still be in the spirit of the competition if you wanted to substitute a modern 8K EEPROM, as long as you kept it to 8K, which is the ability of the processor. Okay.
But when is this gonna be judged?
So actually, I didn't finish. It passed in January.
Oh, okay.
But there were 3 guys who signed up, and so if we tried, he sent me like a huge box of all these nice electronics components as like a participation prize, I guess.
Yeah.
But I started it and I want to finish it, so I'm still working on it. Okay, so this is interesting. This is the schematic from a Atari 2600, the old video game system. And it was really minimalist. It only had 3 ICs on the board, which are these. And the interesting thing is that one of them is 6507, and the other one is the RAM and I/O chip that guy sent us. So I thought that was kind of cool. 2 of the 3 chips in Atari is what I'm putting in my calculator. There's a screenshot of it. This is the firmware running in my simulator on my website. So as you can see, there's floating point numbers. There are a couple of different data types. There's strings up to 8 characters, and then there are like 16-bit hex numbers, basically.
No. Where does this software come from?
Well, I just wrote the software myself.
You wrote all the floating point processing and everything yourself?
That's right, I did.
Sounds like a lot of work.
That's why I missed the January deadline. That's why I'm not done yet. And then the input line you can see here, this is a 4th program because you can program the calculator in 4th. That's the language I chose to make it programmable. So it has 4 data types, so 12-digit floating point numbers. And this is something I really put a lot of work into. I wanted the implementation to be exactly like the HP calculators. So for all of the rounding, I extensively tested it against my HP 48 to make sure that I always rounded exactly like that. Because for me, this was something very, very important for this project. Like I said, it has strings up to 8 characters, and then it has 16-bit hex numbers, and it also has another 16-bit type, which are garbage collected pointers. And this is kind of a departure from 4th, because 4th usually, first of all, you don't have types, and you also don't have any type of garbage collection. So when you define variables and programs in 4th, once you define something, if you want to delete something you've already defined, you're usually stuck with it. You can't go back and reclaim that memory. But on a calculator, that doesn't really work. You need to add and delete variables. So I came up with a scheme to do garbage collection. So when you take a pointer to an object, whether that's something that it's stored internally for the address of one of your variables, or a pointer that you get from the system, it has three things. It stores the base pointer, it stores an offset into the pointer, and then the sum of those two things. And then if you add or subtract from the pointer to step through memory, it will record how far into memory you've stepped, and it will update the total, so that if you try to fetch the data pointed to by that pointer, it will use that sum. Then when you do garbage collection, if the base changes, because it kept the offset, it can update the sum so that the pointer continues to point that many bytes past where it used to point before the pointer was garbage collected. That probably sounds like a whole bunch of stuff that's hard to imagine. But basically this gives me a way to add and delete any program or variable I want and not lose memory.
So basically it sounds like what you really have are regions of memory with the offset, so you can garbage collect and move the region.
Right, right, yeah, like compact things down.
Yeah.
That's right. Okay, so here are the words that I've defined so far. So you have stack operations, just basic math stuff. I've implemented cosine, sine, and tangent with Cordic, and almost done with arctangent, but my program is now 9 kilobytes, which will not fit on an 8 kilobyte chip, so I need to go back and optimize before I finish that. I can do logic on those 16-bit types. You can define programs with forth. They have conditional and loops. These are kind of the standard, most of the standard loop constructs from forth. And then as far as variables go, I did that a little bit differently. If you use this word var to create a variable, and then you use the word stow to store into the variable, then you never have to worry about the pointers to the variables. And usually in forth you have to manage your own pointers, which is very dangerous, because if you make a mistake and write the wrong pointer, you can crash the calculator. And so if you stick to these two green words for all your variable stuff, the calculator should never crash. On the other hand, if you want to do low-level stuff, you have the traditional forth words that let you read and write any part of the memory, or also execute any address. Okay, and so this is like the progress I've made so far. I want to finish adding my Cordic functions, all the logarithms and square root, that type of stuff. I have the system in place for the garbage collection. All my pointers are set up. I just haven't done the function to delete things. I'll need to do some kind of simple graphing to consider it a graphing calculator. And since I have so little space, probably won't be too extensive. And then make everything fit into 8K. Like I said, I'm already 1K over, but I have some ideas about that. Because the computer supports forth functions that the user can type in, you could just rewrite part of the firmware in forth and store that, and that should give you a really big space saving. Okay, so that's my second thing I wanted to tell you about. And then the last thing I wanted to work on was verifying those floating point numbers, because like I said, I put a lot of work into that because I want it to be just exactly like a Saturn processor does. And so I have a lot of edge cases that I do when you're right on the very edge. Which way does it round correctly? Or what if you work with the largest number you can store, or the smallest, or 0? But to be double sure of this, I wanted to generate a ton of randomized data, and then I wanted to compute what the result should be to get a known good result, and then do the same calculation on my calculator, and then I want to compare them to make sure, to check myself and make sure I get it right. And so the difficult thing about this for me was this second step, compute what the results should be. So I thought about, well, how can I get really the right calculation from an HP48? I thought, well, what if I make a bunch of randomized calculations, send the file to emu48, do the calculation, and then pull it off of the emulator. And I tried this, but I didn't get very far. And so what I thought would be really great is if I could use something like Python. But as you guys all know, the problem with doing floating point stuff in Python is because it's stored in decimal, you get these rounding errors. So what I found was if you tell Python that you want to use a decimal number, it will do the calculation internally as decimal, the same as a calculator. What you can also do is tell it how many digits of precision you want. You can configure it to 12, just like an HP48. You can also select the rounding mode to be round to even, and then it will do the exact same type of calculation. So then what I came up with was I would generate this randomized data with Python. I would compute the result using the decimal package to make sure it's just like a calculator. And then I would do the same calculation on my firmware running in my browser, and then I would compare the two to make sure it's the same. The problem I ran into, though, was when I did more than a few calculations, I would generate like a 200 megabyte file and then try to load that in my browser, and then all my browser windows would crash. So what I did was I took my simulator, which is running in my browser, and then I ported it to run in Nodejs, which lets you run JavaScript programs in a console window. And so that has no problem loading a 200 megabyte file. And this is the output from what it did. 56 billion cycles took that many seconds to run. And then that's the equivalent of a 20 megahertz 6502. And so that's actually not that fast, since the real machine runs at 14 megahertz. And the reason why this was so slow is because I was watching YouTube and actually also making this PowerPoint presentation, so my computer was doing other stuff. So if I let it run overnight with nothing else running, it goes up to about 60 megahertz, which is not bad. But then also my laptop got really hot and the fans would come on, and so I eventually got an old Linux server that I would run it on, and then the speed goes up to about 80 megahertz. It's a little bit of a speed upgrade, but also my laptop is not monopolized by doing this. But then I thought, like, even though 80 megahertz is really good for doing my testing, what could I do to make this faster? So I thought about the steps you go through when you're simulating the 6502. So first you'd load the instruction, then you advance the pointer to the instructions to the next one. So next time you do a load, you're in the right place. Then you need to somehow decode the instruction and jump to the function that will do the simulated functionality of that. Perform the instruction, then you have to set the processor flags, and finally return to step one and do the whole thing over again for the next instruction. So if you look at this, the only thing that's really doing anything useful is number 4, maybe number 5, that's important too. But all the rest of these things are just overhead. So if you can eliminate all of these things, then the speed of the simulation should increase. And so the way I came up to do that is, instead of doing this interpretation every cycle, instead I would convert the 6502 instructions into x86 instructions, which then run natively on my Linux computer. So then there's no overhead of interpreting anything, it's just all native code. And so to do that, since I'd never done x86 assembly before, I just compared the instructions, and as you can see, a lot of them, they're the same name, they do the same thing. Some of the other ones, they have slightly different names, and they don't work exactly the same, but for the most part, there's a one-to-one correspondence between the 6502 and the x86. Like I showed before, that 6502 has 4 registers, and the x86 has 16 of those. And those are 64-bit registers, but you can address each of them in an 8-bit mode and treat it like an 8-bit register. So from there, you just map them to these. I have one register for scratch address calculations, and then R12 holds the decimal flag. And then the last thing was to look at the flags that get set on every instruction. So the carry, negative number, overflow, and 0, they're equivalents on the x86. So far so good. We have similar instructions, similar register mapping, and the same flags. So if you look at an example, this is not anything useful, it's just an example I made to illustrate how it works. The first instruction will add 5, and then it will take the result and AND that with 7, and then it will branch if the carry is set. If you look at the x86 version, it's essentially the same, also adding, also ANDing, and then it will jump if the carry is set. So the same type of instruction. The interesting thing though is if you look at the flags that each of the instructions set. So I put an X here because the add instruction changes all 4 flags. The AND instruction only changes the N and the Z flag. So whatever the C flag is set to, the AND instruction will ignore it. It won't modify it. So then when you get to the branch if the carry is set, it's still intact from the add instruction. However, if you look at the x86, that AND instruction always zeroes out the carry, which means that that jump if carry is set will never actually jump. So this is not, it's not a valid translation because of the difference in flags. So what you have to do, I won't explain each instruction because that's probably boring, but basically what you do is you save the carry flag, you do the AND instruction, and then you restore the carry flag so that when you get to the jump, it does the same thing as the 6502 code does. And so this works. I got this working. When I ran it on a sample, it ran at the equivalent of 440 megahertz, which is pretty good. But as you can see, the extra instructions, that adds a lot, and it really slows things down. So I'll show one more example. This is also just a made-up example, but in this one we're going to clear the carry flag, set it to 0, do the same AND with 7 as the last slide, and then we'll do an add instruction. And the add instruction depends on the carry flag. So in this example, we set the carry to 0, we save the 0, and sets the carry to 0, and then we restore it to 0, which is redundant. So we can actually leave out the saving and the resetting since we know it's 0. So if you know what instructions come before and after, you can optimize away some of the saving and the setting of the flags, which I haven't finished this part, but this I think is going to add a lot of performance when I finish this.
So are you looking ahead at the code around it? Is that?
Right, so basically I look for sections of code, and anytime I see a label, I stop optimizing because I don't know where it's coming from, so I don't know what the processor status is. And anytime I hit a branch, I stop optimizing. So then I get a chunk of things, and if I can see what comes before and after, I have a markup file I'm working on to say what things depend on what and what can be optimized out on mine. And the last thing I also want to do is, for example, this is a 16-bit add on a 6502. And the reason it's so many instructions is because the processor can only add 8 bits at a time, so you have to do it in 2 steps. And so the conversion to x86, it looks very similar, but the x86 actually has no problem adding 2 16-bit numbers in one cycle. So that's another optimization I want to add, is identifying things that can be done more effectively on the x86. So that's it for my presentation. My future plans are to finish my calculator. The 6507 calculator, I need to shrink down the firmware, add a few more features, and then, like I showed, that really nice modern 6502, I'd like to create a version for that. Maybe I'll add some more features since I can use more than 8K of ROM and more than 2K of RAM. I think it'll be more fun to use. And then the other thing I'm really interested in is porting it maybe to a PIC32 microcontroller, which would be really fun. And so this last thing I showed where I'm converting the assembly language, maybe it's kind of overkill if I'm just testing randomized floating point numbers, but it's good to have that framework in place because I built it to be kind of generic so I could use it with other architectures. So it should just be a configuration file I change if I want to generate a binary that will run on different architectures than x86, like a microcontroller. So that's it for my presentation. Thank you guys for your attention, and that's my website if you wanted to play around with any of the 4 games that I've ported, or play with BASIC or Forth, or my calculator firmware. You can do that in your browser. So, thanks.